Hello, chemistry students. As you can see, I am not here today. So we're going to do this lesson online. There is something that you will have to upload at the end to prove that you did what I wanted you to do today, and that will count as your attendance. So if you don't upload, it's like you weren't here, even if you're online listening to this. Some announcements before we begin. On the screen right now, the quiz will be open on Tuesday after school when people have had a chance to take it. If you did not do well, and we're talking under 60% at this point, I have put you into a win on Wednesday. Osterberg C is the code to get in at 10 a.m. If you didn't take the quiz, you will take it during win time today. Haley, I think you're the only one that didn't have a chance to take it. Please check your email in there somewhere. And then the retake assignment is currently posted. And the retake date will be May 7th. That will be the last day you can retake. The retake assignment is posted in Google Classroom. It is right here, retake assignments. So if you don't want to retake, you don't need to do that. All right, so we are going to talk more about this thing called stoichiometry. So the question for today is, how do I use a chemical recipe? And the answer is stoichiometry. So some of you might be saying, well, what is stoichiometry, Miss Osterberg? Well, that's a really good question. So stoichiometry is used in chemistry a lot, but it's also not just used in chemistry. For instance, bakers use a stoichiometry when they're making bread. So let's say that as a baker, you knew you were going to need you were going to make 1,000 loaves of bread in the month of May. You don't want to overbuy anything. You don't want to overbuy ingredients. So what you do is you say, okay, I know I want 1,000 loaves of bread, and you work backwards and you say, well, how much do I need of each ingredient? Because remember, we have these ingredients in certain ratios when we make things. To make bread, you might need 4 cups of flour, 4 or 2 tablespoons of oil. You probably need some teaspoons of water. You're going to need some yeast, maybe like 4 ounces of yeast. So you have all these ingredients to make maybe 1 loaf. And so you need to know how many you need for 1,000 loaves. So it's using these ingredients, the coefficients, we've been talking about them, to know what the correct amounts are going to be. Hairstylists use this too when they want to mix colors for chemicals. And I bet if you went to your hairstylist or you went to your baker and you said, hey, tell me how you use stoichiometry, they would look at you like you were crazy. But they are doing that. They just don't understand or know what the word is. So again, stoichiometry is a fancy word for knowing how much you need or want or can get. And it's not just used by chemists. So in our example, the last time we met, we had a double bacon cheeseburger. And so this is what was needed to make the double bacon cheeseburger: a bun, 2 cheeses, 4 bacon, 2 patties. And I said, hey, let's make 5 of these. And so we had to look at the coefficients, which we determined were the ratios. And so for a bun, it's super easy, right? Because you need 1 bun for every double bacon cheeseburger. So it's a 1-to-1 ratio. So in your head, you probably will like, well, it's 5, Miss Osterberg, because if you need 5 double bacon cheeseburgers, you're going to need 5 buns. And I showed it as a calculation because I like to be thorough. So I know that we need 1 double bacon cheeseburger on the bottom to cancel with double bacon cheeseburgers to a bun on top. And that left us with 5. So when we wanted 5 double bacon cheeseburgers with cheese, this is a 2-to-1 ratio. And so the double bacon cheeseburger is going to cross out the bottom because every time we have 1 double bacon cheeseburger, we need 2 cheeses. So if we want to make 5, we're going to multiply. Same thing with the bacon. It's a 4-to-1 ratio. So if we want to make 5, we have to multiply by 4. And a lot of you were just able to do this in your head. and that's fine. The reason I'm showing you this is that it is going to get a little bit more tricky, and we'll come back to that in a moment. We further went on with the mole ratio to talk about, well, how many times would this reaction maybe run? And we had said, well, what if this runs 100 times? And then I said, well, what if it was going to run 538 times? And then I said, well, what if we ran it 6.02 times 10 to the 23 times, which is equal to a mole, right? And so you multiplied, if you have an N2 right here, the coefficient in front is 1, we just don't put it. And so if we had 1 N2, and we wanted to run it 6.02 times 10 to the 23 times, that would just be 6.02 times 10 to the 23. If we have the ratio for 3 H2, so every time we run this, we need 3 parts H2 to 1 part N2. Well, we took 6.02 times 10 to the 23 times 3, because if we were going to run it, we would need it 3 times, so that was 1.81 times 10 to the 24. And if we were going to make 2 for our ratio of ammonium, which is NH3, we would take 2 times 6.02 times 10 to the 23, and that got us 1.2 times 10 to the 24 molecules. And because we're running it a mole of times, these become our moles. So that was our eureka moment that, yes, these are coefficients, and so this is 1, 3, and 2. And before we had written this out as 1 molecule, then to 3 molecules of H2, 2 molecules of NH3. And that's not wrong to say, but the way we're going to use them from now on, because ratios can kind of mean anything, we're using it as we have 1 mole of N2 to 3 moles of H2 to 2 moles of NH3. So we're going to switch gears right now, and we're going to go on to this stoichiometry packet. So the stoichiometry packet, if you are in class, you are actually getting this, and it looks like this. It's going to look like this, and we're just going to do moles to moles. It is actually big. It opens up, right? Okay, we're going to be using this for a couple of days. If you are not in class right now, you are going to go to Google Classroom, and you are going to print this off. And I would print it off if I were you. If you can't print it off, then just be very careful with taking your notes. You probably are going to want to write down some of the questions that I ask, and that will require you to kind of pause the video and then write down the what I'm going over. So make sure that you either print that off or that you have that in front of you at this point. So let's go back to the notes. And again, you can pause it and go print that off and then, put it back on when you're ready. So one thing, I know it says Unit 7, but this is actually Unit 6. It was a typo from last year. So moles to moles. So the mole ratio is the ratio between 2 chemicals, coefficients. So 2, 5, 4, and 2 are our coefficients in a balanced equation used as a conversion factor. So number 1, and this is the most important thing, is you always want to make sure that your equation is balanced. And I'm going to tell you this, if it has numbers in front of it, we have balanced it correctly. Okay? If there's no numbers in front of it, like all of these are gone, then you probably might want to see if it's balanced. Okay? But if there's numbers in front of it, you're good. All right, so just like the double bacon cheeseburger example, let's go over this. So the first thing you want to do is you want to see what you have and what you're going to get. So it says if you have 10 moles of C2H2, so we have 10 moles of this C2H2. How many moles of oxygen gas are you going to need? So we want to know how many moles of oxygen gas. So we're going to write 10 mole of C2H2, and you need to write the chemical because we're going from one chemical to another chemical. So we have to start writing the chemical. And then we're going to do our ratio right here. So our ratio between C2H2 and oxygen is 2 to 5. So we're going to say, okay, we know that every time we do this reaction, we're going to need 2 moles of C2H2, because remember, coefficients now stand for moles. And we're going to also need 5 moles of O2. And this is our ratio. This is our ratio. And so that allows moles of C2H2 to cancel. And so if we take 10 times 5, that's going to be 50. Divide by 2, that gets us 25 moles of O2. 25 moles of O2. So now we want to say, okay, how many moles of, we're going to do the second one. And so this one, it says how many moles of oxygen gas. So again, we want to know how many moles of oxygen gas are needed to react completely. And that just means that we're going to get all of the oxygen and all of this to be used up. Needs to react completely with 3.6 moles of C2H2. So now instead of 10 moles, we have 3.6 moles. So again, we're going to start with the number. 3.6 moles of C2H2 is given in the problem. And we want moles of oxygen gas. So again, we're going to put 2 mole of C2H2 on the bottom. And we're going to put 5 mole of O2 gas on the top. And again, we're going to take 3.6 times 5 and divide by 2. And that's going to get us 9 mole of O2 using the ratio. So it says, what ratio did you use to determine this? Well, that was the ratio of 2 C2H2 to 5 O2. And you can write it 2 ways. You can write it as 2 C2H2, I should put moles here, over 5 mole of O2, or you can write it as 5 mole of O2 over 2 mole of C2H2. You can do both. In our equation, we required the 5 over the 2 because we were starting with C2H2. But if we were starting with the 5O2, if we were starting with oxygen, it would have been flipped. So ratios can be written as either or. All right, so then let's go on to number 2 here. So number 2, we have another chemical reaction. We want to make sure it's balanced, and it does look indeed that it is balanced. So again, we're looking for what is given in the problem. And so it says, based on the reaction above, how many moles of oxygen, so we want to know how many moles of oxygen are required to react complete with 9 moles of aluminum. So we have 9 moles of aluminum right there. So we're going to start with 9 mole of aluminum. And we know that we need 4 aluminums for every 3 oxygens. So we're going to put 4 mole of aluminum on the bottom, and we're going to put 3 mole of O2 on the top. And so we're going to take 9 times 3 and divide by 4, and to 2 decimal places, because whenever you're given decimal places, you want to do 2 decimal places, the 100th place. Moles of aluminum cancel. That's going to get us moles of O2. So if we have 9 moles of aluminum, we also need 6.75 moles of O2. We need both of these amounts to be able to make Al2O3, aluminum oxide. So now what I want you to do is I want you to try to do B and C. So please stop this video and then do B and C.